This is based on joint work with Don Archie and Chris Phillips. I saw that Don's in the audience. I'm not sure if Chris is yet, but Don, if I say anything really stupid, feel free to interrupt me and correct me. Hopefully,
I always do, Julian.
Thanks. Okay, so just a little bit of notation set up in case some of these things don't get said. Just a few points here. Inclusions of subalgebras are unital. We have homomorphisms of compact metric spaces. Alpha can be an action of a group on a C-star algebra or on the continuous functions from a space X into that C-star algebra, and this kind of won't be commented on necessarily. It can kind of get used both ways, used and abused a bit. And the cross product is denoted C-star, G, D, alpha. G will mostly be the integers. There are a couple of theorems that apply in other circumstances, but I think I've stated most of it in terms of the integers. So that's just a little bit of notational stuff. So what's the actual setup we're interested in here? Let's go back to the beginning, namely the case of commutative cross-product C-star algebras or transformation group C-star algebras. So if we have a compact metric space and a homeomorphism on that metric space, then we obtain an action on C of X by composition of a function with the inverse of the homeomorphism. And then we look at the cross product generated by C of X and a unitary U, which implements the action. We obtain the transformation group C-star algebra associated to the corresponding dynamical system. And I think it's an understatement to say that these C-star algebras have been studied extensively and that they've driven a large kind of corner of the theory. Here is a few results, and let's emphasize very few results of the many that exist, but just I think takes us through a nice little historical tour. So perhaps one of the first major results along these lines came from Ian Putnam, who showed that if you have a Cantor minimal system, then the cross product is a simple AT algebra with real rank 0. And it's not just the result that's important here, but also the approach, which we'll see on the next slide, that Putnam introduced and has really become, in some sense, one of the standard approaches for studying these sorts of cross products. Then you have extensive work through, say, the 90s and early 2000s by, among others, Ching Lin, Chris Phillips, Huaxin Lin, and many others. So this Phillips here by Huaxin and Chris is just an example of the sort of results that were obtained, which shows that if you have a finite dimensional space and enough projections, then the cross product has tracial rank 0. And then proceeding from there, there are more general results due to Tom's inventor and many others. But one of the most general results is due to Elliott and Yu, which says that if the dynamical system has mean dimension 0, then the corresponding cross product is stable. And so, like I said, this is just a little scratching the surface of the results that have been obtained studying essentially the commutative case, so cross products arising from minimal dynamical systems. So, as I mentioned, Putnam really introduced the machinery that became the sort of standard approach for studying these sorts of cross products, which introduced this idea of what we sometimes call an orbit-breaking subalgebra. So you pick a compact set Y, and you look at all the functions. This should be C star, not C. All the C star algebra generated by the continuous functions on X, and all the functions which vanish out Y multiplied by the generating the standard unitary U, which implements the action. And so the basic idea here is that A sub Y is easier to understand than A. You can do a Rockland Tower construction based at Y, and this gives you a nice way to understand this orbit-breaking subalgebra, or sometimes called approximating subalgebra. And then the other basic point here is that if we make the right choices of Y, then A sub Y is a large subalgebra in A in an appropriate sense, and therefore properties of A sub Y pass to A, and also when we take direct limits of such things, properties pass to the direct limit and then to A. And so Chris Phillips had the idea of, well, what about trying to abstract this notion? So rather than working with it specifically in the case of where you have this dynamical system and the associated Rockland Tower construction and so on, can you find an abstract formulation for the way in which A sub Y sits inside of A that could be useful not just in the case of where we're looking at C-star algebras arising from dynamical systems, but can be used more generally? And so the definition of a large subalgebra is given here. I don't really totally want to bore you with the details, but the basic idea is to take an arbitrary collection of finite elements and arbitrarily small positive elements in both the subalgebra and the full algebra and find elements which are close to the ones you chose and a positive element in the subalgebra that is large in an appropriate or small in an appropriate sense, where the cut downs by 1 minus that are large, where it's small in a Kuntz sense with the small in terms of it's dominated by the elements you chose in both the original algebra and the subalgebra, and so on. And then you can introduce the idea of being centrally large if it approximately commutes with the set of finite set of elements that you chose. There's also a notion of what we call a large subalgebra of cross-product type. I won't put that up there. I just want to basically make a point that the usefulness of this definition is that it does abstract what the properties you see of the elements that exist in this orbit-breaking subalgebra in the commutative case and how they relate to the full cross-product C-star algebra in that situation. So just as here's a few results about large subalgebras to kind of give an idea of that this definition is useful. Well, first of all, it is the case that the approximating subalgebra in the transformation group C-star algebra is large in the transformation group C-star algebra. So in this sense, then this does generalize what you want, and it's true for a large number of choices of the set capital Y. The classic version of this capital Y is just a single point or sometimes 2 points, but in fact it works so long as the orbit of Y does not intersect itself. So a couple of theorems that Chris proved in his initial work on large subalgebras is that the restriction map on the tracial states is bijective, and then the two algebras, the large subalgebra and the full algebra, have the same radius of comparison. And some more recent work from Don Archie and Chris Phillips is that if you have a centrally large subalgebra, so you have this additional approximate commutation condition, then if this centrally large subalgebra has stable rank 1, then so does the full algebra. And if it has both stable rank 1 and real rank 0, then the full algebra has real rank 0. The two conditions here are needed for technical reasons. I'm sure Don would like to get rid of the stable rank 1 condition in part 2, since you'd want to not have to need that, but it's used in their methods. Okay, so the idea is, well, let's define the same type of orbit-breaking subalgebra, but replacing C of x by C of x comma d, which you can, of course, identify as C of x tensor d. And so the idea is we have continuous functions from x whose values are in some C-star algebra D. All right, and so if we want to study cross products of such things, the idea would then be to use the same sort of large subalgebra machinery that works in the commutative case and develop theorems that allow us to apply this in this situation. So we'll start with the question is, when is A sub y large in A in this set? So here is, in addition to the useful setup and information at the start, so we assume that the set Y is small in the sense that it doesn't meet its own orbit. We assume that the automorphism in C of x d lies over homeomorphism H. And what this means is just that if you restrict the action of alpha to C of x, so in other words, C of x tensor 1, that it arises, it induces a minimal homeomorphism of H. So this should say a minimal homeomorphism. In most cases in this talk, if I say homeomorphism, minimal should probably be there, but there will be a situation later we'll point out explicitly something is not minimal, and we'll have to fix that. Alpha is what's called pseudo-periodically generated. I'll mention what this means in a moment. And then D is either simple and has a tracial state, or is simple and purely infinite. So we break, of course, this up into two situations: the tracial state case and the purely infinite case. So with that setup, then A sub y is a large subalgebra of A of cross-product type. And in the tracial state case, you can show that it's centrally large. And we'll see later why the centrally large, that additional condition is useful in this situation. Now, in the purely infinite case, things actually work out easier. And you can show that both A sub y and A are purely infinite in this situation. Did I say? Oh, yeah. So A was on the previous slide. Just to be clear, if I use it like this without stating it, A is just a shorthand for the cross product to not have to write the entire thing out. So the cross product of CXD by this action alpha. Okay, so what does pseudo-periodically generated mean? It's not really a particularly interesting definition. It's mostly just a piece of just terminology that makes it easy to not have to keep stating the same property over again. Oh, in the chat, is D unital? Yeah, D is always a unital algebra in these situations. And in some cases, it may be assumed to be simple, and I may just forget to put that in, but it's definitely always going to be unital. Okay, so the main thing with this pseudo-periodically generated is to identify some more natural situations, natural conditions on D where it's satisfied. So if D is purely infinite, this is automatic. If D has strict comparison of positive elements, you get this pseudo-periodically generated condition. If D has property SP and order on projections is determined by quasi-traces, then you'll have this condition. There are also a few others. If the OT D is, if everything in OT D is inner, I believe is one of them. Or you don't even need to be quite that strong. If you have a, essentially the subgroup of OT D that alpha generates, powers of alpha generates is inner, that's another example. But the ones in the ones down below here are, in some sense, the kind of things you would encounter for a lot of the choices of D you'd be interested in looking at. So I just wanted to highlight those conditions. Okay, so to make use of this, what we end up doing is we want to combine this large subalgebra idea with some additional structure that these orbit-breaking subalgebras have. And to do this, you essentially proceed again in kind of an analogous way to the commutative case. So you define the appropriate analog of recursive subhomogeneous algebra, which we call a recursive subhomogeneous algebra over D. And oh, Chris just said approximately inner. Sorry, not, okay. Yeah, I thought I was saying that incorrectly, but yeah, from earlier. So yes, you define a recursive subhomogeneous algebra over D, which simply means a definition that looks exactly the same as the definition for a recursive subhomogeneous algebra, but instead of your coefficients or your outputs being in Mn, they're in Mn of D. So you simply replace just n by n matrices with n by n matrices that have entries in D. And then everything kind of works through in a very similar way. So one nice result is that if you take a strongly self-absorbing C-star algebra and D is stable in the appropriate sense, the typical thing here is to use script D, but of course we're already using letter D, so I use script E. So script E stable if this should be D, not A. Sorry, I'm probably notation change somewhere happened. So the main point here is consider the case of particular interest right here is the case where this is Z, the Jiangsu algebra. And so the idea here is that if you start with D and it's simple, separable, and Z stable, then a recursive subhomogeneous algebra over D is also Z stable. And so that's the particular situation we're going to want to use here in a moment. So if you take Y to be a closed set with non-empty interior, then the orbit-breaking subalgebra is a recursive subhomogeneous algebra over D. In particular, and this is used later in some examples, if X is the Cantor set, then you have essentially an isomorphism between A sub Y and a direct sum of the following form. The Y sub K's are totally disconnected. And so what you end up with essentially is something that looks like a direct sum of AF comma D algebras, you might call them. Essentially a direct sum of things which look like AF algebras tensored with D. And so this gives us a nice result later on. So the idea here is to connect the recursive subhomogeneous structure with the large algebra structure, because the condition here that the interior of Y be non-empty, well, that conflicts with the condition we required earlier that the iterates of Y not intersect themselves under the homeomorphism H. And so the idea is that if you start with a closed set Y, you can find closed subsets whose intersection is Y, and A sub Y is a direct limit of the orbit-breaking subalgebras A sub Yn. And in particular, if Y is a closed set whose never meets its own iterates, it can be expressed as the intersection of closed sets with non-empty interior. So this ties the two concepts together. in that situation, A sub y is large, and it's a direct limit of recursive subhomogeneous algebras over D. So you get the same type of situation that you get in the commutative case, where the approximating subalgebra A sub y or A sub a single point y is a direct limit of such things, which are recursive subhomogeneous algebras in the classical sense. So if we combine together these observations with the observation on stability over a strongly self-absorbing algebra, what we see is that for any closed set y, A sub y is E stable. In particular, well, if D is E stable, so in particular, if D is simple, separable, unital, and Z stable, Z being the Jiangsu algebra, then so is A sub y. And of particular note here is that this doesn't require an assumption on the dimension of X or even on the mean dimension of the system. And in fact, as we'll see later, we'll have an explicit example where the system has positive mean dimension and the cross product is Z stable anyway. And we're going to get that here in general in a moment, but that's the idea, is that the Z stability or E stability, we also have an O infinity example, comes entirely from the fiber algebra D, not from the dynamics. So if you have a inclusion of a centrally large subalgebra into another C-star algebra, and the centrally large subalgebra is tracially Z-stable, then so is A. This is a result of Don Archie, myself, and Chris Phillips in a previous paper. And then if A is nuclear, you obtain this for Z stability without the tracial condition. So in that case, if A is a nuclear C-star algebra and B is a Z-stable centrally large subalgebra, then A is also Z-stable. And so in particular, applying this to the situation where D is simple, separable, unital, nuclear, and Z-stable and has a quasi-trace, then the full cross product, not just the orbit-breaking subalgebra, but the full cross product is Z-stable and has nuclear dimension at most 1. So in this case, we obtain nice cross products. They have nuclear dimension at most 1, and without any requirement on the dimension of X or the mean dimension of the system. So this is essentially entirely then coming from the Z stability of D. Now, in the non-Z stable situation, here we'll need to make some assumptions about the space X and or the dynamical system XH to obtain any good structure results on the cross product. Now, to kind of take full advantage of this recursive subhomogeneous algebra over D idea, we need an answer to the following question. What structure properties do simple direct limits of these recursive subhomogeneous algebras over D have? So for instance, what conditions on D would guarantee that the such a simple direct limit has real rank, stable rank 1, real rank 0, and potentially other things? So the idea is then to do the analogous theorems that Chris proved in his initial work on direct limits of recursive subhomogeneous algebras. This requires, among other things, the right notion of a diagonal map between algebras in the system, and this is some ideas for future work. For now, we can make some progress by, in some specific examples, in both the Z-stable and the non-Z-stable situations. So if we have a homeomorphism which has positive mean dimension, but D is Z-stable, that was essentially the result of the previous theorem I discussed. If X is the Cantor set and D has stable rank 1, if X is the circle, H is an irrational rotation, D has stable rank 1, real rank 0, and trivial K1 group, and if D is purely infinite and simple, we can, in these situations, come up with some general results as well as some specific examples. And perhaps the most noteworthy thing about the examples, of which I'll show you a few in a second here, is that most of our examples do not seem to be attainable using previously known general results, and I'll point out a few such reasons. So in one case, if we have a C-star algebra D, which has a strict comparison of positive elements, a tracial state, and stable rank 1, and if X is the Cantor set, then the resulting cross product has stable rank 1. If, in addition, we assume it has real rank 0, then the cross product has real rank 0. And this mostly follows from the observation I made earlier that the approximating subalgebra, the orbit-breaking subalgebra, is a direct sum of things that look like AF algebras tensored with D. Another result is that if X, that should be D, not X. If D has stable rank 1, the dimension of X is at most 1. So yeah, okay, that got repeated somehow. And D has stable rank 1 and real rank 0, then K1 of D is 0. Order on projections over D is determined by quasi-traces, then the stable rank of the cross product is 1. Sorry, I must have done some copy pasting and this got all mangled up. But the basic idea is that this works outside of the counter set case. In the case where the dimension of X is less than or equal to 1, there's some additional conditions on D. Okay, so very quickly, let me give a few examples. I'm not going to go through the details, partly because I'm running out of time. But in this case, if you start with an infinite product of the circle and you take the forward shift, now this is where I mentioned it's not minimal and it has mean dimension 1. And you take D to be the 2 to the infinity UHF algebra and you pick an appropriate automorphism of this algebra. Okay, so how do we deal with the fact that our homeomorphism is not minimal? You make an identification and you choose the minimal subshift that Giel and Kerr introduced in their paper on cross products with perforation in the dynamics. Then in this case, we can choose a minimal subshift that has mean dimension arbitrarily close to 1. Then we can find an action on CXD. And the cross product in this case is Z stable by the earlier theorem, even though, of course, in this case, the dynamical system has positive mean dimension. So the idea here is to give a specific example where this occurs. So that was of the first sort of type that I described where we can make some progress. And the point here is that, again, the mean dimension being greater than 1 makes this sort of example hard, inaccessible from a lot of the previous work that had been done, which tended to assume that you have mean dimension 0. Now, here's an example of the second type. Take X to be the counter set, take D to be the reduced C-star algebra on the free group on infinite many generators. Define automorphism of that free group to just be the forward shift on the indices. And then take a tensor product of that automorphism with the automorphism on C of X, then this has stable rank 1. And no previously known results say anything about this sort of cross product structurally. And in particular, this action has the Rockland property, but that does not appear to help. I'll skip over this one, but here's an example where you obtain stable rank 1 and real rank 0. And in particular, the example is constructed in a fairly complicated way using model theory to find a certain subalgebra. But besides having stable rank 1 and real rank 0, it's also set up in a way where the cross product is designed not to be Z stable. And finally, an example of type 4. So take the minimal subshift from earlier. Take D to be O infinity, but the generator is indexed over the integers. Take alpha to be the gauge automorphism, and then alpha sub zeta to be the gauge automorphism, and then alpha to be the corresponding action on CXD. Then in this case, the cross product is purely infinite, simple, nuclear, and O infinity stable. And this is another situation where previously existing general results don't seem to say anything. So the results at Hirschberg, Winter, and Zacharias can't be applied because there's no reason in this case we would expect alpha has finite Rockland dimension with commuting towers. I suppose it's possible that it may, but it doesn't seem to be likely. So that's the idea then is we have a bunch of other examples as well. I just wanted to put up a few, but there's definitely examples here that can be accessed using our methods that don't seem accessible from previously known results. So thank you very much.